Okay. Hi, everyone. So, first of all, I don't want you to be disappointed. I will not be presenting anything new regarding compilation techniques. The only thing I will be presenting is just a mere report of what we have observed as a result of compiling to WebAssembly. So first, I will start with a gentle introduction for those of you that are not extremely familiar with WebAssembly. So although some of these aspects have already been presented, I will still go with my slides. So Wasm is a virtual machine that has been, I think, initially designed for running fast applications on the web. It's an open standard, meaning that there are several implementations that are compatible one with each other. It's a low-level VM, and we will see that in details. It's type-safe, great. And it has no standard library, which is kind of unusual, especially if you compare to the JVM, which has this use set of Java classes. So the core language of WebAssembly is low-level arithmetic operations. It's a stack-based structure. You push and pop values from the stack, but you have global variables and you have temporaries. You have functions, and we will see that. It has a standard binary format. It has a tool chain where you can compile, assemble, disassemble, profile, debug, these sort of things. And it has two external syntaxes. Let me dig into this particular aspect. What you see here is an implementation of a recursive Fibonacci function expressed in WebAssembly. So sorry, just one end, not easy. Here you see the regular Fibonacci function. You have a parameter x to a function called fib. In WebAssembly, all user identifiers are prefixed with a $sign. And here we make the comparison of this parameter x with 2. If it's smaller than 2, we return 1. Otherwise, we compute x minus 1, and we make the recursive call and the second call, and we sum up, and we are done. The same thing, exactly the same program, we can implement it with this S-expression-like format, which is absolutely equivalent, and it gives you the illusion that there is a structure in WebAssembly, although it's just exactly the same thing as before. And by illusion, what I mean is that actually I can have 3 parameters to the call of fib, and it's fine. I will just be pushing 3 values, and fib will be popping 2, but since I have added this add thing here, I will pop the extra value, and everything is fine. So you see the two formats are absolutely equivalent. Also, when you are using a Lisp-like system for implementing something related to WebAssembly, this format based on S-expression is extremely convenient because you get the parser for free. And so we are very happy with that. Okay, so WebAssembly is pretty small, but on top of the WebAssembly machine, you have a full-fledged extension over there. And the ones that are interesting for us, compiling dynamic languages, are probably exceptions that we need here. Where are exceptions? Exceptions are over there. And of course, garbage collection. It's a very useful extension that comes with a type hierarchy. And we have also things that we like very much in the Scheme community, which is tail call and these sort of things. So let me present that. The garbage collection extension, it comes with a hierarchy of type that are now available on Wasm programs. And this hierarchy is you have a general type, you have a subtype of it, which is a type of values that are comparable with the EQ predicate, and you have subtype for that. How do you use this thing? Here is an example of the implementation of Lisp lists, if you want. You define a pair type, which has just a car and a CUDA, which are 2 references of any values. And here is the implementation of the list copy function, where you take as parameter a list that might be empty, and the empty list here is represented by the null value. Then you are able to check if something is a null value with this predicate here. If it's null, you return another null value. Otherwise, you access your list, and I will try just with one end. Here it is. We extract the car of something, and the way you do that is you say, I'm considering the local parameter O. I will extract the property car of something which is a pair. And on top of that, I will put that in a new pair that I allocate with this struct new thing. And this is provided by the garbage collection extension, which is great because now it's very close to what we need for compiling Lisp or ML or whatever. So this is not the only thing we need slightly more, and in particular we need another extension, which is function references, which basically give you pointer to function. So next to the previous hierarchy, we have the func type and funcref type, which is just pointer to function. So pointer to function is not closure. So if you want to implement a closure, you will have to use some encoding similar to what you would be doing with assembly or C code, which is you will have to build your own data structure for closure, which is what we do here. Oops, sorry. Here we define the type of closure, which is just a pointer to a function and an environment. And here we implement the scheme function for each, which accept a function and a list, and we apply the function to all the elements of the list. And this is exactly what we do here, where we call the function. From this data structure, we extract the entry point, which is pointer to function. But since Wasm is safe and is type safe, we have to cast this into a function which will take two arguments, the environment and the actual value. So this is a cast here. And now we can call this pointer to function, and we are applying the function to all the elements of the list. Great. With that, we are almost happy. The last bit we are missing is a connection with the outside world, because at some point we will need to implement our library. And what we have been using in our settings is external value using JavaScript value. And the way you do that is you have this new type, extern and extern ref. And in this example, I show you how you can manipulate a JavaScript bignum from within JavaScript. You will declare a type, which has an extern ref as a payload, and then you will refer to JavaScript functions that are accepting as argument an extern ref. And here I'm implementing in Wasm a predicate that tells me if a bignum is 0 by just invoking the JavaScript function which is there. Okay, so far so good. Sorry, I have been fast. Now, what we have been doing with Wasm is checking what's going on with managed languages when they are compiled to Wasm. And by managed language, basically what we mean is languages that use garbage collection and that are either functional or object-oriented languages or dynamic languages. The kind of languages we like. So we try to collect all the language we could, but we restrict ourselves to real language that are not experimental, language that are meant to implement real application, if you like. We also restrict ourselves to languages that are decently easy to install. We didn't want to go to all the hassle of installing all these crazy things. Robust implementation. We want to be able to run kind of actual benchmarks. And something important for us, we wanted multi-backend systems because we wanted to compare the performance of compiling to WebAssembly versus compiling to pre-existing backends, so native code or something like that. Okay, so these are the language we have been able to put our hand on and that we have been able to play with. So let me start with GHC, which is Haskell. So here is the performance of Haskell compilation when compared to native Haskell. The red line is a native Haskell compiler, and the blue bars are the ratio in between what you get with Wasm and with native compilation. So the first observation that we have to make here is that the GHC implementation of Wasm is extremely robust because all the benchmark runs, which is kind of great. But you have to pay a price, which is something like a 8-time ratio when you are comparing the performances. We didn't do any reverse engineering, but what we have understood here is that Haskell is not using the garbage collection extension, so it is using everything by itself. So it is implementing its own stack, its own GC, its own everything. So our guess is that if you are not using the extension, the 8x ratio is something that you have to be ready to pay for if this is the way you want to go. So the other implementation we try is Dart. Dart is easier to install because when you get Dart these days, you get all the backends of Dart without any extra operation that you have to do. So you get a native code, once again, the red horizontal line, and you get also a JavaScript backend and a Wasm backend. And so what you observed here is that Dart is decently robust, mostly all the benchmark runs, and you get more or less same kind of performance as you can get if you are using the JavaScript backend. Although JavaScript, for some reason, seems to have a problem implementing bignums because e-digits and pi-digits are using bignums, so maybe there is something weird with the implementation in JavaScript with bignums that makes somehow the whole picture that I'm presenting here not totally fair for JavaScript. But still, you see with Wasm, you have more or less the same performance. If you are really interested in building web application and you want an extensive connection with JavaScript, not sure that it is so interesting to use Wasm as of today. Maybe you can stick to JavaScript. It's kind of up to you. So the other language is Ruby. So as you can see, Ruby is not as robust as what we found with Dart because half of the benchmark are not really running with this, in this language. And you see the kind of performance you can get. It's in between 2 and slightly more than 10x if you are using Ruby. And once again, it's just a Ruby that you can download and install on your machine and run the benchmark, and this is the kind of thing you will observe. Then the next beast is OCaml, and OCaml is interesting because it has several backends. And first thing, what I'm comparing to here is OCaml-C, which is not the optimizing compiler, it's a bytecode compiler. So I'm comparing JavaScript and Wasm to the bytecode compiler for OCaml, and the reason why we are doing that is that JS of OCaml and Wasm of OCaml are actually based on the bytecode compiler. So we thought it was a fair comparison. And what you see with the purple bar are the performance of OCaml native compiler. So you have all this performance in the same in this picture. And what you see is OCaml is extremely robust. It compiles very well, and actually there is no missing thing. Sequence actually runs with Wasm, but for some reason that we have not been able to understand, it runs infinitely fast. And it really runs. That is, it produces a good result, but extremely fast. And we have not been able to understand why. Maybe because the JIT is playing some tricks and there is some memoization or something like that. I don't know, but this is it. So you have good performance, not exactly as good as what you can get with a native compiler, but it's quite usable as is. Next system is Guile, which is a scheme implementation. And it's not the easiest one to install, as I must say. Maybe not so robust either, because 2/3 of the benchmark only runs. But Guile aims at being a complete scheme implementation with support for call CC and all this sort of bells and whistles we have in this language. So maybe this explains also why the performance of Guile is not so great in comparison to the native compilation, because you have to pay some price for manipulating the stack and so on and so forth. The last implementation is our implementation, another scheme implementation, but without support for call CC. So maybe it's a reason why we are able to be much more robust and much faster. And one of the interests of our implementation is that it's able to compile to native code, red line, to JVM bytecode, and to Wasm bytecode, and to Wasm code, sorry. So you see that it's quite comparable to what you get with JVM, which sounds like a remarkable result if you consider the expertise that has been put in the JVM and in Wasm. And for us, we see this as a very promising result. So in comparison, just this table, and you see that for at least 3 languages, maybe there is something weird with OCaml. So let's say at least with Dart and Bigloo, we are in the range of 1.5x to 2.x compared to native code for Wasm, which is kind of really great because you have some benefits in addition to the performance. So the other thing that we did is to try several possible compilation strategy, and we try to measure the impact of all these possible ways you have to generate Wasm code. So the first thing which is kind of striking with Wasm is that it is basic block unfriendly. And what I mean by that is you don't have go-tos in Wasm. So if you represent your program as a call graph and just branch in between basic blocks, you will be doomed. You have to do something else. So typically, a normal compilation would look like something like that. You have a trampoline, and you have a local variable representing your program counter. You will just have a main loop, and from going to one basic block to the other, you will assign your program counter, you will loop, and you will just use a switch table to go to the next basic block. Hopefully, you can avoid this schema by using the technique presented in this great paper by Norman Ramsey that tells you how you can take your control flow graph and reconstruct the loop that you have probably had in the first place in your program. And we measure the cost of using this technique or not using this technique. And you see that basically, if you do not do this relooper technique, you will have a slowdown close to 2 on many benchmarks. So if you have one idea to keep in mind is that if you have to implement only one optimization when you are generating Wasm code, is implement relooper. The next thing we did is try to see what is the impact of using i32.1 ref. And these are just small fixed nums of 31 bits. So if you are willing to accept small integers only, what will be the benefit in comparison to allocated fixed num of 64 bits? And the performance is as follows. For most benchmark, there is no real penalty in allocating your fixed nums. And the reason for that is normally you use your fixed num for array indexes or these kind of things, and you can pre-allocate these small fixed nums. Only benchmarks that use big small fixed nums, such as Fibonacci, have to allocate them, and then you will start paying the price for that. The other thing we try is there is a great option in V8 is that you can run WebAssembly in an unsafe mode. If Andreas was in the room, he would have said this is no longer Wasm. Okay, but for us, it's interesting to have a fair comparison with C, and C, you can compile unsafe code and things like that. So it's interesting for us to make this comparison. And you see that if you accept to have your program that crashes from time to time, well, you may have an acceleration of 30% or something like that. So this is maybe interesting for you. Then the last aspect I would like to present is type safety. This is a normal implementation of the scheme car function. What you do is you test that the value you received is really a pair, and if it's a pair, you access the car, otherwise you trigger an error. You may think that a normal implementation of Wasm would be this one. You test if your value is a pair, which is the thing I'm doing here, and if it is a pair, you access it, otherwise you throw an error. No, it's not that easy in WebAssembly because WebAssembly is safe and it is not relying on occurrence typing or anything of this kind. So you have to test that something is a pair, you raise your own exception, otherwise you have to cast the value into a pair, and this may trigger an internal error. So actually you will be testing twice if the object is a pair. So what we have tested is what is the price we pay for this double testing, and here it is. That is, we generate code without any type test introduced explicitly by our compiler, and this is what you observe. So this is a kind of a limitation of WebAssembly. There is a technique for getting rid of this double test, which is using branch on cast here, that we have not implemented yet, so I cannot report on the benefit of using this instruction, but normally you should be able to get rid of this double checking. Okay, so I'm almost done. Some final thought for concluding this talk. First thing is we see this platform as a platform very promising because we are able to get close to 1.5 regarding Bigloo as a penalty in terms of performance, and other systems are in the range of 1 to 2 when compared to native code, which is kind of remarkable. You have this idea of compiling once and running everywhere, and yes, indeed, it works. We are able to compile once our scheme program and to run them on the server and to run them on the browser, which is kind of wonderful. We are still missing some features, and in particular, we have no call CCs in Bigloo because we don't have basic operation for manipulating the stack. We don't have multi-threading, something that we miss. Implementing our runtime library is kind of a pain because we are missing things. We are relying on JavaScript, but the scheme library provides blocking I/O operation, and it's not easy to implement that when you just have non-blocking operation with JavaScript, so it's kind of a limitation. There are, for now, operations that we cannot implement. And there are some, I think, interesting problems. The problem is the not connection between traps, internal Wasm error, and exception that force you to have some double checking. So I think that for type safety, we can avoid that. But for instance, for array bound checking, you cannot avoid that. You have to test that your index is in the array, otherwise you trigger an exception of your language. And then Wasm will also test that the memory access is safe. So I think it will be difficult to get rid of all this double checking always. Then it's really low level. It's really just a bare machine without any library, without anything. So it means that you will have to implement your own linkers and loader, which can be kind of a little bit painful. And maybe one of the obstacles of compiling, it's not really generating code, but it's because you are lacking library, you will have to re-implement your library by hand. And regarding our implementation, it's about 50,000 lines of Wasm code that we have written by hand. Thank you so much for your attention.
Interesting and really broad study. I wanted to ask about your comparison. So I think you're comparing sets of benchmarks, and actually different sets of benchmarks for each language against the native compiler for that language. What happens if you take, say, one benchmark and compile it to Wasm with all your different tool chains? Which one does better? I mean, can you say something about the quality of Wasm code generation for the different languages, or not really?
Not really, and we are not interested in comparing one language with the other. We just wanted to compare just the performance of what is supposed to be the best possible compilation for each language. So we wanted to compare GHC to GHC, OCaml to OCaml, and we wanted to avoid any war of...
is not interesting.
To me.
Were you able to measure the startup time and tiering time? So for compiling, the startup time for your benchmarks?
No, we didn't. We pay attention to have benchmarks that run at least 10 seconds each. So probably the startup time is minimal and negligible. So yeah, we are using long execution time. And what I didn't mention is that we measure actually 2 Wasm implementation, something you will find in the paper. So it's not only one implementation. Yeah.
Hi, so being from JetBrains, you must ask, why didn't you include Kotlin in your comparison? Is there any reason for that, or?
For not implementing, which language you said?
Kotlin.
Maybe we didn't think about it. We should have, I'm sorry.
It was interesting to me about the importance of using the GC and using the same stack. Those two things, though, are kind of separable. Do you have any thoughts on how you might test them separately, or will it just depend on having the right sort of implementation where you can pull those apart?
Could you be more specific in your question?
Right.
What do you have in mind?
Two of the things you talked about for Haskell, for example, is that they're implementing their own GC and their own continuations, right? Their own use of the stack, right?
Yeah, somehow, yeah.
So you could imagine that maybe you're doing those two things differently, right? That in some other language implementation. Is there some way to peel apart the importance of reusing the GC versus reusing the continuations?
No, I don't know. The only way maybe to answer this question would have been to implement our own GC for our own scheme compiler. I think this would have been too much for this report. So no. The only evidence that I can provide is that apparently implementing your own GC with Haskell, performance-wise, is not so great. And for Bigloo, the GC extension apparently works very well, because 1.5, I was not expecting such a good result considering the maturity of the platform and the extension. So that's the only thing I can say.
Okay, thank you.
Thanks.